Infectious diseases exhibit different dynamic patterns. A pattern of relatively stable incidence of infection or disease over time is called stable endemicity. Some sexually transmitted infections, like HIV in USA, shows this type of behavior. There are roughly 50,000 new cases a year, and this number have remained fairly constant during the last decade. Many waterborne and respiratory infections exhibit seasonal endemicity because transmission rates vary with environmental conditions. For these, incidence may vary a lot within a year, but less between years. Cholera and seasonal influenza are examples of such diseases. Stable and seasonal endemicity are normally associated with diseases against which acquired immunity is ineffective in either clearing the infection or preventing reinfection. Immunizing infection with relatively short infectious periods, in contrast, often exhibit epidemic cycles with recurrent outbreaks spaced out by predictable inter-epidemic periods. Many of the vaccine-preventable childhood infections shows this type of dynamics. Measles, for example, historically had major outbreaks every 2 years in most Western countries. Whooping cough incidents typically peaked every 3 to 4 years. The susceptible infectious removed model revealed that the epidemic cycles are due to what ecologists call consumer resource interactions. For an infectious agent, susceptible individuals represent the resource that can sustain the chain of transmission. Transmission from an infected individual, the consumer, to a susceptible individual, the resource, result in a new infection. The infection thus converts the resource into more consumers, much like a predator converts prey into more predators when it feeds its young. Consumer resource interactions generally have a propensity to cause population cycles, and we see this borne out in many diseases. Key characteristics resulting in population cycles are high transmissibility, short infectious period, and transmission blocking immunity upon recovery. The reason is that when such pathogens enter a susceptible population, they spread very rapidly, converting more and more susceptible individuals into infectious individuals in an epidemic of growing momentum. However, the short duration of the infection means that the infectious individuals rapidly become immune. After a while, the epidemic begins to recede because of the resource depletion, much like a forest fire ebbs as it is burning out of fuel. The next epidemic cannot take off until a critical number of new susceptible individuals have been born. The intra-epidemic period, which is often very predictable in large cities, is determined by the birth rate of the host and the transmission rate of the pathogen. Increasing either of these characteristics leads to faster cycles. For measles, we saw a manifestation of this in many European countries after the Second World War. During the baby boom, birth rates increased by as much as 30%. There followed a decade of annual epidemics before the birth rate returned to the normal of about 20 births per 1,000 individuals per year, and the intra-epidemic interval reverted to major outbreaks every 2 years. Vaccination effectively reduces the number of susceptible individuals born into the population because immunized children directly enters the removed class. Mass vaccination, therefore, often increases the inter-epidemic period. Measles, for example, used to cause annual outbreaks in Kenya before the implementation of routine and supplemental vaccine activities. During the last decade, measles is largely absent, but have caused major outbreaks every 5 years or so. Theoretical models have shown that some level of seasonality in transmission rates are necessary to sustain population cycles indefinitely. The epidemic cycles of childhood infections are generally sustained by the seasonality in contact rates caused by aggregation of children during the school term. Historical records from Britain shows that measles transmission was about 3 times faster during term time than holiday time. Predictable population cycles occurred for at least 2 centuries and probably for as long as cities have been around, ending only when vaccination became so prevalent that the susceptible pool very nearly dried out.